Hi everyone, hope everybody is staying well, keeping yourself safe and healthy. Okay, so we're going to talk about chapter 8. We completed chapter 7 last week, and you guys did an exam, and all of you did really wonderful. Okay, so congratulations. So, in the chapter 8, we're going to learn about electron configuration and chemical periodicity. We're going to learn characteristics of many electron atoms, quantum mechanical model and the periodic table, trends in three atomic properties and chemical reactivity. So in the last chapter, we learned about three quantum numbers, and this is a summary of quantum numbers that we had learned. We learned the principal quantum number, the symbol was given as n, and the permitted values were 1, 2, 3, and we can go up to 7 since we have 7 periods. It tells us about the orbital energy and also the size of the orbitals. Okay, and then we learn about angular momentum quantum number, which we gave the symbol L, and it can go from 0 to n minus 1. Okay, and orbital shape. So this tells us about the orbital shapes, and the values for L could be 0, 1, 2, 3, and they correspond to S, P, D, F orbitals. Okay, and then the third quantum number that we learned is ML, and that is an integer that can go from minus L to 0 to plus L. That tells us about the orbital orientation, and also it tells us the number of orbitals possible for each kind of orbital, right? For remember, we have for S orbital we have 1, and for the p orbitals there are 3 orientations. So there are 3 p orbitals possible, and for the d we have 5 orientations, meaning there are 5 d orbitals possible, remember. And then the last one that we're going to learn today, a new quantum number, we call it as a spin quantum number. Now the first 3, n, l and ml, that describes the orbital. Okay, and the fourth quantum number spin, we give the symbol ms, that talks about the electron, that specifies the electron. So it can take values plus half or minus half. Okay, could be plus half or minus half, and this tells us about the direction of the electron spin. You know, electrons are negatively charged, so we can consider them as tiny magnets. So in the presence of a magnetic field, so the electron can align either along with the magnetic field, or it can align opposite of the magnetic field. In other words, it could be clockwise or counterclockwise. If it is facing upwards like this, the first one we call that the electron has spin quantum number plus half. Okay, and if it is facing opposite to the magnetic field, like the arrow facing down, we call that the spin quantum number is minus half. Okay, so electron can be any of these orientations, and then we give that as a spin quantum number. It could be plus half or minus half. So this example, so the diagram shows us over here the effect of electron spin. So you have a beam of hydrogen atoms. Okay, and when the beam of hydrogen atoms passes through a non-uniform magnetic field, it splits into 2 beams. You can see it splits into 2 beams. Okay, half of the electrons are attracted by the large external magnetic field, and while the other half are repelled by it. So as a result, they are going to separate into the 2 types of spins. One is ms minus half, the other one is ms plus half. Okay, so the sum of the electrons could be taking the spin plus half, and some would be minus half. That is the electron spin. Move. Okay, quantum numbers and the exclusion principle. Now we have learned 4 quantum numbers. Basically, with these 4 quantum numbers, we can specify any electron in any element in the periodic table. Okay, each electron in any atom is described completely by a set of 4 quantum numbers. First 3 quantum numbers describe the orbital, which is your n, l and ml, while the fourth quantum number, your ms, describe the electron spin. Now when we are placing electrons in the orbital, we have to follow some guidelines. And then the first one that we're going to learn is called the Pauli's exclusion principle. It states that no two electrons in the same atom can have the same 4 quantum numbers. Remember, we learn about 4 quantum numbers. If you take one element, no two electrons in the same atom can have the same 4 quantum numbers. At least by one quantum number, they have to have a differentiation. Okay. And another rule or a guideline that we're going to follow, atomic orbital can hold a maximum of 2 electrons and they must have opposing spins. Okay, so the polar exclusion principle, and then also we have to follow that only 2 electrons can be in one orbitals and they have to have opposing spins. Let's look at this one with the example of hydrogen and helium. Okay, so if you take hydrogen atom, hydrogen has 1 electron, correct? So it's in the principal quantum number n equals 1. If hydrogen n equals 1, L value is going to be 0 to n minus 1, so L going to be 0, and ml going to be again 0 because ml is going to be minus L, 0 plus L, right? So ml is also going to be 0. And then the ms is a spin quantum number. So this 1 electron could be facing up. That is the ms. In fact, as a convention, that when we put our first electron, we always face it upwards. So making that electron ms going to be plus half. So these are the 4 quantum numbers for the 1 electron in hydrogen atom. Normally, we can represent an orbital either with a circle like that, or we can represent an orbital with a box like that, or we can represent orbital with just a line like that. So that's the first electron for the hydrogen. Now if you want to find out the set of quantum numbers for the helium atom, so I'm going to do some modifications here. So the helium has how many electrons? Helium has 2 electrons. So for the 2 electrons for the helium, oopsie, I need to erase this guy here. No, how am I going to erase it? Okay, got it. So helium has 2 electrons. So the first electron for the helium is going to take the same quantum numbers like hydrogen. Now this is a different atom, right? So this is MnL and this is your Ml. Okay. And for the helium, first electron also has the same quantum numbers just like the hydrogen, 1 electron, 1, 0, 0 plus half. And then the second electron for the helium, because it has 2 electrons, that should also go to the same orbital. Because if you take one orbital, it can have maximum 2 electrons. Do you see that? It can have maximum of 2 electrons. Maximum of 2 electrons, and they must have opposite spins. So now if this is the orbital, so the second electron of the helium also goes to the same orbital, but we have to have the opposite spin. Okay, so the second electron is going to be like that. I'm going to put it in the same orbital but opposite spin. Now if you write the quantum numbers for the second electron of the helium, n is going to be 1 because it's still in the principal quantum number, n equals 1. And if n equals 1, the same L value, L going to be 0. ML going to be 0, but for the second electron, MS going to be minus half. Okay, so now do you see the Pauli exclusion principle that states no two electrons, go back, no two electrons in the same atom can have the same 4 quantum numbers. Now, the first electron and the second electron, they differ at least by ms value. Okay, they have 4 different quantum numbers. So that's what the polar exclusion principle states. Okay, any questions? I guess I cannot hear you. And the maximum of 2 electrons, and they must have opposing spins. That's the polar exclusion principle. Okay, so then let's move on to the next slide. Factors affecting atomic orbital energies. Energies of atomic orbitals are affected by nuclear charge, shielding by other electrons. So we know that the atomic orbitals are going to be outside of the nucleus. So this orbital energy can affect by the nuclear charge. What do we have in the nucleus? We have protons in the nucleus. They are positively charged. And then the electrons are in the outer orbitals. They are negatively charged. And we know there is an attraction between nucleus and the electrons. Positive, negative attract to each other. And then there's another thing called shielding. So the shielding is also going to affect the orbital energies. A higher nuclear charge increases nuclear electron interactions and lowers sublevel energy. If it has a lower sublevel energy, meaning it is harder for that atom to lose an electron. Shielding by other electron reduces the full nuclear charge to an effective nuclear charge. Z effective. We'll talk a little bit more in detail what is this effective nuclear charge. Z effective is a nuclear charge an electron actually experiences. Also, orbital shape affects the sublevel energy. So what are the 4 shapes? S, P, D, F. They all have different shapes. Remember, S looks like a spherical sphere, and then P looks like a dumbbell, and then the D look like a butterfly. So their shapes also affect the sublevel energy. Now this diagram shows us the effect of nuclear charge on the sublevel energy. Higher charges interact more strongly than lower charges. Therefore, a higher nuclear charge, meaning more protons in the nucleus, increases nuclear electron attraction and thus lower sublevel energy, meaning it stabilizes the atom. We can see this effect by comparing the 1s sublevel energies of 3 species with 1 electron. So we are seeing 3 different atoms here. The first one is the hydrogen atom. Hydrogen atom Z equals 1. You see, hydrogen Z equals 1. And then we have helium plus iron. Helium plus iron meaning helium has 2 electrons, plus 1 means it has lost 1 electron. But its nuclear charge is 2 because it has 2 protons in the nucleus. And then we can look at lithium. Lithium 2 plus. So lithium atomic number is 3. And if it loses 2 electrons, it becomes lithium 2 plus. but it has Z equals 3 because Z is the number of protons. Okay. So this diagram shows that the 1s sublevel in hydrogen, meaning one proton attracting one electron, is the least stable, meaning it has high energy. It is 1311. And then if you look at the helium, the energy is 5250. If you look at the lithium, to remove that one electron, we need to give 11,815 kilojoules of energy. As the nuclear charge increases, going from +1, +2 to +3, it's getting harder for that one electron to lose. Okay, so the least energy is needed to remove its electron is going to be the hydrogen. Excuse me. Excuse me. And the 1s sublevel in lithium 2 plus, 3 protons attracting 1 electron is the most stable. So the most energy is needed to remove its electron. So that is the effect of nuclear charge on the sublevel energy. Greater nuclear charge lowers sublevel energy. It takes more energy to remove the 1s electron from the helium plus than from the hydrogen. And similarly, it's going to take more energy to remove 1s electron from the lithium 2 plus compared to the helium plus. Okay. Shielding and orbital energy. So shielding. So what is shielding? Electrons in the same energy level shield each other to some extent. Electrons in inner energy level shield the outer electrons very effectively. In many electron atoms, each electron feels not only the attraction to the nucleus but also repulsions from the other electrons. Normally, repulsions counteract the nuclear attraction somewhat, making each electron easier to remove by, in effect helping to push it away. We speak of each electron as shielding the other electron to some extent from the nuclear charge. The further from the nucleus an electron is, the lower the Z effective for that particular electron. Shielding effect is the phenomenon where the valence electrons are shielded from the attraction towards the nucleus. So here we have two cases again. Shielding by electrons in inner energy levels. Now in the first example over here, when we compare the two atomic system with the same nucleus, one with inner electrons and then the other without. The ground state lithium atom has 2 electrons. So the first one is the helium and then you have the lithium. So we call it as a ground state lithium. It has 2 inner 1s electrons and 1 outer 2s electron. So this is your 1s 2 electrons and this is 1 2s electron. Okay, and then if you look at the lithium 2 plus, lithium 2 plus means 2 electrons. So this electron in the very outer shell is easy to remove because there is a repulsion from these 2 electrons. Once 2 electrons has been lost, you are left with 1 electron. Now it's making it very hard to lose that 1 electron because there are no shielding from the inner electrons. So earlier, to remove 1 electron, the outer shell, it needs only 520 kilojoules of energy. Now in the 1s orbital, to remove this 1 electron, it needs 2954 kilojoules of energy. Okay. And same thing here in our helium. Helium has two electrons, but then the same energy level, two electrons, they repel each other, making it easier to lose one electron. Once it lost, you have only one electron and there is no repulsion because there is no more electrons to repel. Now there is a greater interaction with the nucleus, making it harder for this electron to lose. Penetration and sublevel energy. So we learn about the sublevels, which is your SPDF, and these SPDF energy levels, they also have different energies even if they are in the same level. So this diagram shows us the radial distribution of the electron density. So the first one is the 1s, which is more closer to the nucleus, and then the 2s, you can see there is a hump here, and then this is the distribution for the 2s orbital, and some part of the 2s is very closer to the nucleus, whereas a 2p orbital is your brown graph. Okay, so now the 2s and the 2p, both of them are in the same principal quantum number. But you can see here 2s sublevel is more stable than the 2p because it penetrates closer to the nucleus. As it is more closer between the 2s and the 2p, 2s would be lower in energy compared to the 2p, and we call it as penetration. Orbital shape causes electrons in some orbitals to penetrate closer to the nucleus, and that is due to the shape of the orbital. Remember the shape of the s and the p orbitals? What is the shape of the s orbital? It's spherical in shape, whereas the p orbital takes this shape. So that's why we see this kind of radial distribution. Okay. Penetration increases nuclear attraction and decrease shielding. So S is going to be more closer. So as a result, 2s would be lower in energy compared to 2p orbital. So when the electrons are being filled up, in the second energy level, 2s will fill first and then goes to the 2p sublevel. Okay. Splitting of energy level into sublevels. Each energy level is split into sublevels of different energy. Splitting is caused by penetration and its effect on shielding. For a given n value, for a given principal quantum number n, a lower L value indicates a lower energy sublevel. So the order of sublevel energy is SPDF. Lower L value. L for the S is 0, 1, 2, 3. So the lower L value indicate lower energy level. S would be the lowest energy, and then the P, and then the D, and then the F. So this diagram shows the filling of energy sublevels with electrons. Now we're going to put electrons in these orbitals. And then it's going to fill up based on the energy of the orbitals. In general, energies of sublevels increase as n increases. Energies of sublevel increase as n increases, just like 1, 2, 3. And as L increases, SPDF. As n increases, some sublevels overlap. So 1 is going to be the lowest energy level. When the electrons are being filled, it's going to first fill up the 1s level. And then it goes to the second level. So in the second level, you have 2s and 2p. And between 2s and 2p, we know that the 2s is lower in energy compared to 2p due to the penetration. And then when you go to the 3s, we have in the third level, we have 3s, 3p, and 3d. And it says here, as n increases, some sublevels overlap. We would expect 3s, 3p, and goes to 3d, but now you see 4s right there. between 3p and 3d. Again, that's due to the penetration. So we will see some overlap as we increase the principal quantum number. Okay. Okay, great. So this is a wonderful place to stop the first part of this chapter. And I will conclude the first part here, and then we'll start in a separate video how to fill up the periodic table according to these rules that we learned today.